Hi, welcome to chapter two of computer organization and design. And in this chapter, we are going to study the MIPS instruction language. And basically, it will be the machine that we will use forward in this class. So we need to understand a bit this machine. We are going to talk about mainly, let me go to the next slide here. We are going to talk about mainly the instruction set architecture. The instruction set architecture. What do we mean by the instruction set architecture? Well, in this course, the purpose of this course, we are designing a microprocessor. And this microprocessor, we are going to explain certain concepts and operations and optimization. So we need some sort of an example machine. So in this case, we will use the MIPS machine, and this MIPS machine will be the example machine that we will carry with us. And this machine has many types. One of them is the R3K or R3000, a bit old machine, but enough for us to use it as example of the concept that we will study in this class. Now, let's go back to the earlier instruction. So while we are here, what do we mean by the instruction set architecture? Well, here is what we mean by the instruction set architecture. The instruction set architecture basically is the interface between the software world and the hardware world. So here lives our microprocessor. Okay, our microprocessor is in the motherboard here, and it understands the language of zeros and ones. Okay, basically it executes operations on the data. The operations are expressed in terms of ones and zeros. The data is expressed in ones and zeros. Now, who is driving these things? Well, we have to drive this microprocessor to do what we want to do through the instruction set architecture. So the instruction set architecture are those knobs that allow me to operate the microprocessor. If you take, for example, the car as an example. So here's the car, the automobile. Okay, I'm not good at drawing, but this is the automobile, for example. Okay, this is a door here, and this is a door. Bad drawing, I know, but if you look at this automobile, how are we driving this automobile? Well, we need some kind of a steering wheel. Okay, and we need some kind of gas pedal and brake pedal and etc. So these are the knobs to allow the driver to use these knobs so that the driver can operate the vehicle. Those knobs are the what we call here the instruction set architecture that allows the programmer, right, to operate the microprocessor and the hardware subsystem. Okay, so the instruction set architecture are those knobs. Okay, so and it separates the software world from the hardware world. Anything below the instruction set architecture is hardware, anything above it is the software. And that's why it is very important that we explain the instruction set architecture, because these are the knobs that are going to operate our microprocessor. Okay, so let's keep going here. So what do we mean by the instruction set architecture? What are there to explain? First of all, the very first thing is the instruction set architecture tells me what are the instructions that I can execute on this microprocessor. In terms of computation, do I have add, subtract, multiply, etc., etc.? What kind of load store instructions I have? What kind of jumps? Okay, branch of equal, jump instruction. What kind of floating point operation? What kind of memory management instruction? So the instructions, the assembly instructions that I have are the one key part of the instruction set architecture. The instruction set architecture, that's one part. The other part is the registers. So as a programmer, especially using assembly programming, I need to know what are the registers that I have in my machine. Okay, so in the case of the MIPS, I have 32 registers, and then I have three special registers: the program counter, okay, and the high and low registers. The third part that I need to understand about the instruction set architecture is the format. When I encode my assembly instruction, the format that I would encode them to generate the machine code. Okay, so these are the format that I use to generate what? The machine code. The machine code, which translate assembly instructions to machine code. So these three things, the instructions, the registers, and the formats, are the main parts of instruction set architecture. So whenever I describe an instruction set architecture, I have to tell you these three things. And in this chapter, we will cover these mainly three topics. Your author in the chapter will explain a little bit of instructions, then go to registers, then go to formats, then go back to instructions and a little bit more of registers. So they do this kind of looping so that they solidify the concept. You might see some of the things repeated, okay, but that's how they decide to do it in the slides. I'm gonna stick with them because they are good slides. Okay, now, so for example, here we start with the registers. And the registers in this machine are number. They have numbers from 0, okay, to 31, excluding the three special. We said we have three special registers. We're not going to touch them. They are the program counter, they are the high and the low. We are not talking about those yet. We are talking about the 30 registers, okay? And we can refer to these registers as their numbers. So for example, take this register here, which is register $ A0, refers to a register. We call A0 the alias or the name, or I can refer to this register by its number. So I can say register 4. Both are the same. I can do this or that. Okay, take for example register S0. I can say S0, or I can say $ whoops, sorry, or I can say $16. Okay, both are equivalent. Okay, but people like to use the naming because it's easier to deal with names and aliases rather than remember and memorize numbers. Okay, so registers, we have 32 registers. Every register is 32-bit, and every register has a number and an alias. Okay, and we will see more about those registers later, very shortly. Okay, so that's how many registers and therewith. In general, the instructions for MIPS, they can be classified as arithmetic, right? We will have arithmetic instructions like add, subtract. We have data transfer like load, store, both for bytes and words, and half words. Logical instruction where I do the ANDing, the ORing, etc. And conditional branch instruction where I check for a condition, then I branch, and jump instructions. So these are the categories of the instructions that we're going to cover in this lecture, and they are necessary to understand for the rest of the class. Okay, MIPS MIPS instructions. So we talked about the spec thing in the previous job. We said that these are collection of programs which are used to measure the performance of the CPU. Now, in the spec 2008, which is a bit old, but we can see that in the spec end, if we analyze all the programs in the spec end, we will find 16% of the instructions are arithmetic, 35% data transfer, 12% logical, 34% conditional, and 2% jumps. Okay, what's the takeaway here? Most of the instructions are data transfer or conditional jumps. That's the takeaway. And that's why you will see that those are very hard to manage when we go to chapter 4, when we talk about the control. They are common, and at the same time they are hard. Okay, so that's for in terms of. So here are examples of instructions, and again I'm gonna go over these examples and explaining the assembly language of MIPS quickly, because I know you covered a lot of these concepts in an earlier class. I assume that you understand the concept of loads and stores and registers. So we're gonna go in a bit faster mode as we explain them, because we assume that you have certain level of knowledge in regard to assembly language. So data transfer, okay, and notice that he says here I format. What is that? Well, these are the formats that we have. We said part of the instruction language, we have three formats. The format for machine language, the R format, typically for ALU, I format, and J format. So when you see I format, it says that this is the format that it is referring to. Okay, all right. So let's go back to oops. Let's go back to. Okay, so if we do a quick review here, we have load instructions, we have store instructions, we have load byte, we have store byte, we have load half. What's the difference between load word and load byte and load half? Well, load word moves a word which is 32-bit from memory to the register. So whatever word is saved here, we're gonna load it to this register. Load byte, we will load just one byte. Okay, well, the word is how many bytes? 4 bytes as far as MIPS is concerned. And I know this might be confusing because we've studied in the assembly class that the word is 2 by 16 bits. Now we have to change this now, and the word in this class is 32 bits, and which is equivalent to 4 bytes. Okay, and load half, which means 2 bytes. We will load 2 bytes to this register. Okay, how about store? Now we are storing here. We are storing word. We're storing the word into this memory location. We are storing in this case. Oops. Did I do a mistake? This was the load. Here we are storing this byte, the least significant byte into this memory location. And here, when it comes to storing, we're storing the least significant 2 bytes into this memory location. Okay, all right. Now we will talk about this calculating memory addresses later on, but basically, when we have something like this, we consider this as the base address, and this is the displacement. So the effective address equal the value of the displacement, which is 100, plus the value in the base address, which is S2 here. Okay, we have arithmetic instructions where we can have add, subtract, and then we have this add immediate, which means basically, you will see that for arithmetic instructions, we have three operands. The last two are the sources, and the first is destination. So we are adding S2 plus S3, and the result is an S1. Similarly, we are subtracting S2 minus S3, and the result in S1. Subtract. Sometimes the third operand, one of the sources, can be immediate. So now we are saying S2 minus 6, and so 6, this is an immediate data. Okay, and that's why you can see here that this I here indicate immediate data. It means that the second data is in the instruction. Okay, we can do jumps here, jump to this location, jump return, jump and link. So I'm sorry, jump on register, sorry, jump register and jump and link for this. Okay, just a quick preview of what we have in terms of instruction. Now, what we have here, this is the MIPS sheet, and this MIPS sheet, you can use it in the exam, especially to generate machine code, and you can see these are our formats, and you can see some of the opcodes right here, and these are the instructions. Okay, these are the opcodes here, and typically we are not using the second page or the other page. There are or actually this one here, these are floating point, and typically we don't use them. We just generate the machine code for integer instructions. Okay, all right, and these are the register numbering. No one expects you to memorize the register number. Okay. Now, this is the sheet one more time, more elaborative. Okay, now let's talk about the math. We start with the arithmetic instructions. Arithmetic instructions like an add here. Okay, typically we have two sources, all right, and one destination. So in this case, what we are doing, we are adding C plus what is in B and then saving the result in A. That's typically. So we have three operands in the instructions, two sources and one destination. Two sources and one destination. So you can see here in this example, when I say add T0 S1 S2, what is going to happen? That T0 will get the result of adding S1 plus S2. Okay. Similarly here, T0 will get the result of adding S1 minus register S2. Okay, so you can see that this is the kind of format that we are having in the MIPS. And I know for Intel, those who studied simply, you have two operands, but in here we have three operands, two sources, and one destination. Okay, now, okay, whoops. So so for example, if I want to do this expression, right? How am I supposed to compute it? And here, the way I would do it, and obviously here, I don't like this example a lot because I like to assume, for example, these are in registers, okay? But we'll take it as it's right now. So to compute this expression, I need to compute this addition, and so you can see that I'm doing the add and I'm saving the result in T0, register T0, and then I'm doing this add as well, and I'm saving it in register T1, and then by doing a subtract, I can get the value of this function. Okay, all right. Now, um, let's go back again and revise or review the registers. As we have said, we have 32 registers. Each register has a number, so you can see these are the numbers, okay? And we can refer to the register by its number, like so, dollar sign, or by its alias. So $0, dollar sign 0, dollar sign number 0, they mean the same thing. And registers, we have, you can see they are numbered here all the way to 31 from 0 to 30. So we have 32 registers. In programming, we will use the T registers and the S registers quite a bit. So yeah, this is the complete set of the T registers and the A registers for subroutine and the V registers. Okay. So keep those in mind. Again, these are the set of 32-bit registers. We will see more and we'll learn more and more, but you will see in many of the examples we'll use a lot of this. Those are like general purpose registers, and the other ones, they have specialized usage. We might not use them in this class, some of them. Like for instance, we're not going to use the frame pointer in this class or the global pointer. We don't. But obviously, we would use the T registers, the S registers, and in the subroutine, we'll use the V and the A. And always, we would use our friend the zero register. The zero register is a register with a value of a zero all the time. You cannot change its value. Okay. All right. So here comes our example, which we did a minute ago, and now we assume that this value here, which is the f, is stored in S0. Okay, S0, and this one is stored in S1. Okay, and this one is stored in S2, and this one is stored in S3, and this one is stored in S4. Okay, and now you can see that we need to compute f here and save it at S0. So first what I do, I add S1 and S2, which is right here, and save in temporal register, which is T0. Then I add these two guys, all right, and I save it in T0, T1. Then by subtracting T0 and T1, I am subtracting these two sub-expressions and saving it off in the, so notice I'm using what instruction? Add, subtract, okay, all right. All right. So now we'll take a look at the load and store instructions. All right. But before we do that, you know what? Well, let's break at this point. It's a good point to break, and we'll continue the discussion, and we'll in part two. Thank you.